This video clip will describe about one type of input signal that is called pseudo-random binary sequence, or PRBS. This is one of the widely used signal for system identification experiment. The description of the PRBS can be described by the following diagram. All right, it is actually the PRBS sequence obeys an autoregressive equation. The variable x has n states, x1 ... xn, all right? And the equation is the following. The first entry of x, which is x1 t plus 1, the future step is going to be a linear combination. And that linear combinations is given by the coefficients a1 to an. All right, this is the first equation. The second equation is just to pass the previous state to the future state. So here you read that x2 at time t plus 1 is going to be the first state from the previous step. The third state, the future third state, is actually the second state of the previous step, and so on. Okay, and the last one would be xn t plus 1 is xn minus 1t. Okay, and these are state variable in the PRBS signal. Okay. So you see that, okay, the state 1 passed the value to state 2, just like this equation, and so on, okay? And all the states, all right, all the states, x1, x2, and xn are drawn, all right, are observed and multiplied with the coefficients ak, and everything sum up. But we will make a note that the summation here are modulo 2. Okay, this is not a typical addition. It's a modulo 2 or XOR. Okay, so which means this operation, and one thing is that all the coefficients are binary numbers. So AKs are either 0 or 1. And you're going to initialize the states, you know, as binary sequence as well. The initial states are either 0 or 1. The operations here are modulo 2 or XOR, which means 1 XOR with 1 is going to be 0. 1 XOR with 0 is going to be City Park. Do you remember? Sorry. It should be 1, and then 1. And what about 0? XOR with 0?
0.
Yes, okay. So can you all see this, that, okay, if we use modulo 2 operation and the sequence coefficients are all binary, start with binary, everything will be binary sequence, right? So if we progress using this equation, I mean, all of your state values is going to be either 0 or 1. And the output of the PRBS sequence is given by the YT, is given by the n state of xt. Okay. So let me jump. So basically, if you look at this diagram, you will see that, oh, PRBS just obeys state space equation, okay, that has n state variables. The sequence is actually the output of this state equation, but it's a state equation that have XOR operations. So if I jump to the to some examples of the sequence real quick, you're gonna see that it's gonna be, don't worry about the magnitude yet, but it's gonna be it's gonna look pretty random like this. Okay, 0 1 0 0 1 1 1, or okay, and we're gonna see it in more detail shortly. Okay, now let me go back to what we're gonna learn today. Okay, so what we're gonna learn today is that, okay, from this description, we're gonna look at its property, its characteristics, and then what we're gonna focus is the autocorrelation and the spectrum, because as we mentioned at the beginning of this chapter, that when we look at when we get to choose an input signal for system identification purpose, we would like the signal to contain enough information to stimulate the system. So that's why we look at the spectral property. And because spectral property of a signal also related to what? Correlation, right? This is one of the topic I asked you to review. Okay, review of stochastic process and the Wiener-Khinchin theorem. I hope that you watch the video and read the book, okay, according to this theorem. So that's why all the previous lecture, we look at the spectrum, we look at the autocorrelation, and that's what we're gonna do the same for Prbs. Okay, let's start with the characteristic of Prbs. Okay, so as I mentioned, we're gonna initialize the state to be any non-zero state. So x0, at the initial time can be anything. So if n is 3, it can be 0 0 1, it can be 1 1 1, but it's just except that it can't be 0 0. This is not the choice. Okay, the coefficients are either 0 1, or additions are modulo 2. The sequence are going to be two-state signal or the binary sequence. Okay. So do you agree that because your xt is going to be a vector of n by 1, all right, and each entry is either 0 or 1, all right? So Napat?
Yeah.
So if you have n states, all right, and each states are either 0 or 1, what are the number of possible states of x? If n is 2, okay.
2 to the power of n minus 1, because all zero states are not allowed.
Okay, so if we don't exclude the 0 state, of course, the number of possible states is going to be 2 to the n, right? 2 to the n.
Yes. Yes.
Okay. Oh, I think I turned down the volume from my end, but it's still very loud. Okay, so the number of possible states is 2 to the n minus 1. Okay, and then we're going to come back to these two properties, but let us take a look at how the Prbs progresses given by using different choices of feedback coefficients. Okay, so remember that we have this, so now n equal to 3, so the Prbs equation progress like, okay, x3 t plus 1 is going to be a1 x1 t plus a2 x2 t plus a3 x3 t. Okay, so so if I try to write it in vector format, all right, so it seems like you're going to do things like this. Okay, except that when you make a summation here, it's going to be modulo 2. All right, now, and remember that the rest of the equation is like this. Okay. 3 2 1 3 Oh, I think I messed it up with the, did I write the equation correctly? The first one is supposed to be x1, all right? This is x1, this is x2, okay? This is, hold on. x2, okay. This is the first equation, it's supposed to be x1, and x2t is equal to x1t, right? And x3t, x3t plus 1 equals to x2t, correct? So everyone follows this equation. So what I describe is the equation from the description. Okay. Now, now look at this. Okay, this is what we start. This is x at time 0. We start with 1, 0, 0. Of course, so x2 at the next step. So we take a look at x1 here. So x2 is going to be received by x1 from the previous step. And x3 is going to be received by x2 from the previous step. Okay, what about x1? The entry of x1. x1 is going to be given by this equation, right? So if I write the vector A here, 1, 1, 0, okay? And then you do the inner product, okay? If I just multiply element-wise, so it's going to be 1, 0, 0, right? And what you're going to do is you're going to take the modulo sum of all 3 entries. Everyone follow this? Can I touch? So 1 multiply 1 is 1. 1 multiply 0 is 0. Of course, 0 multiply 0 is 0. So Kanatat, what is 1 XOR 0 XOR 0? Kanatat?
Could you repeat the question again?
Okay, what we are doing is we just evaluate the term in the term in the yellow box. Okay, we are verifying that x1 at the time step of 1 is actually 1. So what I did is, of course, I write the vector A here, and then I do the dot product, right? I do the dot product according to the yellow box. So if I multiply element-wise in each element, I get this vector, but then I need to do the modulo 2 operations. I need to make a sum. So that's the question, that what is 1 modulo 2 with 0, modulo 2 with 0?
It's gonna be 1, 0, 0.
No, it's going to be scalar, all right?
Oh.
So 1 XOR with 0 is...
Is 1.
Yes, and 1 XOR with 0 is...
1.
1, yes. That's why we got 1 here. Okay, Kanatat? Okay, good. Okay, and for the next step, we're going to still progress according to this the space equation, which means, okay, we're going to draw the first step, all right? The first entry to the second entry, the first entry to the second one to the third one, all right? This is according to these equations in the red line, and then we do the same for to compute this 0. I hope it's not hard. Okay, now so then again, according to the yellow box, so now I'm going to put the vector A here, all right? And then when I multiply element-wise, okay, total, Can you give me the entries of, can you give me the entries of these two vectors? Multiplication in element wise. Total.
1 1 0.
1 1 0 total. Okay, good. Muhammad, what is the XOR, the results of XOR, the results of modulo 2 operation? Muhammad.
1 plus 1 plus 0.
Yes, but what is the result?
1.
What is 1 XOR with 1? We have the table previously.
0.
Yes, 0. All right. 1 modulo 2 with 1 is 0. But then with this 0 is
0.
okay.
And 1.
0. What is 1?
0 plus 0.
0 modulo 2 with 0 is 0. You have a question?
No.
Okay, so so that's why we got 0 here at the second step of x. Okay. All right, and we just continue. All right, this is just to illustrate how the PRBS sequence progresses. Okay, I'm gonna delete the whole thing, and we just do we just compute according to this manner until you can you observe that until this is the initial step, right? This is the first step, second step, the third step, and then at the fourth step, we come back to no. At the last step is 1 1 0, and for the fifth step we're gonna repeat. If you try to compute right at the fifth step, we actually come back to the previous to the initial state, which means with this example your state vectors has a period of oh sorry, I think hold on. I think there is a mistake on my on the book. Sorry, on the slide. I need to check. Hold on, let us check real quick, okay? If we on the second state, okay, what we, can someone check real quick? At the third state, is it correct? 0 and 1, right? And then, Kanatat, can you compute the third state, is it correct? Can you confirm that this actually is actually 1? Kanatat?
Oh, wait a minute.
Okay, multiply this. Okay, so it's going to be what? Okay, the multiplication of these two vectors.
It's 0.
Okay, is 0, 1, and then 0.
Oh, it's okay. It's 1.
Okay, and when you do the modulo 2, you get
1.
1. Okay, so this state is correct. All right. Now ping, just confirm the last one. This is 1, this is 0. Okay, so 1 1 0 here. And then okay, can you multiply?
So 1 0 0.
Okay.
And modulo 1 0 is 1, and
Okay.
1 0 is 1. Yes, that's correct.
That's correct. Okay, that's correct. Now, so maybe we do it one more step. Okay, now we don't have the answer. Okay, this is the next step is, of course, this is going to be 1, this is going to be 1, okay? Now multiply these two guys, City Park, multiply these two guys gives?
1 0 0. 1 1 0.
Okay, after the modulo 2
is 0. All of them is 0.
Is 0, right?
Yes, yes.
Okay, so we see that now this state is repeated with this one, right?
Yes, yes.
Okay, right? So at the state 5, it repeated with the state 2. Then it means that if we just continue our sequences, it's gonna have a period of 3, right? Period of 3, because you're gonna repeat with these 3 vectors all the time. Okay, is it clear? Now let's change to the other choice. If A is 1 0 1, okay, and we still start with the same initial state. If we do the same process, then at this iteration we would see that, okay, we come back to the initial state. So if we choose this feedback coefficient 1 or 1, the sequence has a period of 7, 1 2 3 4 5 6 7, okay, and that number 7 is actually the maximum period. The maximum period, because we mentioned earlier that you mentioned earlier that there are possible 2 to the n minus 1 different states, right? So for n equal 3 is 7. So it means that in this example, if we choose A as 1 or 1, you reach the maximum period that Prbs could give you. Okay. So let me ask Napat, would you prefer the first or the second choice if you would like to generate pseudo-random binary sequence? You try to wanna have input signal that imitates some random entries. Napat?
I think the choice 2.
Why?
Because it has more uncertainty.
Right, because you try to make it as random as possible, right? Like when you have many possibilities, if you have more possibilities, it means it looks like more random. So that's why we are concerned with what? With the pseudo random sequence that gives you the maximum period, and we have a result. Theoretical result that says, okay, if we, of course, we use Q inverse as a delay operator. If we define the polynomial A Q inverse like this, okay, and then so if we consider this polynomial operator with a sequence yt, of course, if you just write it out, A yt is going to be given by yt modulo with a1 yt minus 1 plus dot plus an yt minus n. Okay, so this homogeneous equation, okay, if you look for any sequence, all right, in a sequence yt that satisfy this homogeneous equation, the statement says that, okay, your solution yt will have a period of 2 to the n minus 1 if and only if these two conditions hold. Okay, so why this homogeneous equation is related to the property of PRBS sequence? Okay, this is because remember when we look at the first equation of the state response. Let me write again. A1 what? A1 x1t, right? A2 x2t dot dot dot. Okay, and then you use the fact that x2t plus 1 is x1t, right? x3t plus 1 is x2t dot dot dot. Xnt plus 1 is xn minus 1t. Okay, so my point is that if you, for example, if you substitute x2 with x1 t minus 1, okay? So from the yellow equation, you can also write that x2t equals x1 t minus 1. And x3t, City Park, can you answer this? I try to write other states in terms of x1. For example, I can write x2 in terms of x1, x3. I know that x3 is a function of x2, but I know that x2 is a function of x1 from this equation. City Park, can you write x3 in terms of x1?
x1t minus 2.
Yes, very good. So you do the same and you plug it back to this equation. Actually, you're going to end up with this homogeneous equation. Okay, it's not hard, just review it yourself, all right? Just plug it in, you will get this homogeneous equation. Then these results, that's why these results suggest that, okay, if you want your state sequence from PRBS to have maximal length, okay, 2 to the n minus 1, it must satisfy your polynomial AQ, which is determined by A1, A2, and AN. Your polynomial AQ must satisfy 1 and 2. Okay, now let's take a look at the condition. The first one says that, the polynomial A is irreducible. Irreducible means it cannot be further factorized by a product of any two polynomials. Okay, that do not exist, the choice of A1, A2, that gives you A. The second condition is that your polynomial is a factor of 1 plus q to the minus m, but not a factor of 1 plus q to the minus p, where p is less than m. All right. Now, let me just illustrate that. Okay, come back to our choice here. Come back to our example. Example 1 and 2. Of course, the first one doesn't give the maximum period of PRBS, right? So the first choice, A110, which means the choice of A110 doesn't satisfy either one of the two conditions. Okay, now I will just kind of illustrate why it violates these conditions. Okay, from this choice of A that doesn't give you the maximum period, the corresponding polynomial is what? Okay, so this is an example of n equals 3. Okay, so the coefficient 1, 1, 0 that correspond to AQ as 1 plus, this is A1, right? This is A2. And of course, this is A3, which is 0. Okay, now I can show that I will just kind of give you a reason that okay, these first one doesn't fit to the maximum period because these polynomial violate the second condition by giving you the example that, okay, I'm going to show that these polynomial, when you multiply with this 1 plus Q inverse, okay, it actually gives you 1 plus Q to the minus 3. Okay, which means it violates this statement. Your AQ inverse is a factor of this polynomial. Okay, it's a factor of 1 plus Q to the minus P, where P is less than M. In this case, of course, P is equal to 3 and your M is 7. Okay, that's why and in order to verify this example, you just multiply the polynomial just like the way you do, but the sum is just the modulo 2 operations. For example, Kanatat. Okay, let's multiply these polynomial. When you multiply the polynomial, of course, okay, let me just give you a sketch, right? So you're gonna get a different term, all right, with different coefficients. So this is the constant term, the coefficients with Q inverse, the coefficient with Q to the minus 2, the coefficient with the Q to the minus 3. All I'm saying that you just do the regular multiplication, but when it comes to the sum operation, you make the modulo 2. Kanatat, the constant term. How do you get the constant term from this multiplication? Kanatat?
Is 1.
1, and you look at 1 and 1, right?
Yeah.
Okay, 1 multiply 1 is
1.
Is 1. There's no other term involved, the constant. Okay, next, Muhammad. What about the term that involve Q to the minus 1? Which term? Muhammad.
Sir,
Muhammad. Okay, so it's gonna, yes.
you repeat the question?
The question is, I'm looking at the results of multiplication according to Q inverse, all right? So I should look at these pair, right? And what else? 1 and this, right? Okay, what's the result?
Q minus 1 multiply 1.
Which is?
Q minus 1.
Yes. You have 1, right? And then what about this term? That gives you 1, right? Okay, but what is the result of modulo 2 here?
Is 0.
Is 0. So that's why you get the coefficient of 0. Okay, Totok, can you give me the coefficient of Q minus 2?
Yes.
So what term do I look at? Here and
Cross Q1 and Q2.
Okay.
1.
So okay, what's the coefficients? So is 1.
1 modulus 2 of 1.
Yes.
0.
Is to 0. Okay, the last one. Who else? Ping. Okay, Q minus 3. Ping.
Yeah. Yeah.
The coefficient of Q to the minus 3 is?
We multiply Q minus 2 and Q minus 1. And yeah, it fall to 1.
It's equal to 1. Okay, so the result is 1 q minus 3. Okay, so I'm just illustrate how to multiply these two polynomials, but the main result is that your AQ, all right, is a factor of this polynomial in the pink area, all right, which means it's a factor of polynomial in the form of 1 plus q to the minus p, where p is less than the maximum length. It violates the second condition. So that's why this polynomial, okay, if you have a homogeneous solution to this homogeneous equation using this polynomial, your solution will not have a maximum period. Okay, so, but of course, we are more concerned with the maximum length, PRBS. So the question would be more like, oh, okay, can you give me a polynomial AQ that satisfy these two conditions? Right? The question would be this way. So we have the results that, okay, we give you a list of polynomial A that satisfy the two conditions in this theorem, and that is a list ranging from n equal 3 to n to 10 states. Kanatat, okay, if I use n equal to 10, what is the maximum length of my PRBS sequence?
1023.
Yes, 1023. Is it a lot? Is it a lot? Yes, it's a lot, right? So now you can see that, oh, by increasing the number of states, all right? And for example, oh, if I use 10, I would just pick AQ. So my A, the coefficient A would be 1, 0, right? 0 and 1, and then 0, 0, 0, all the way, and 1, all right? I use the coefficient, the corresponding coefficient A here, and I just implement the PRBS according to this scheme. And then I get, 2 to the 10 minus 1, 1,000 possible states, all right? And of course, luckily, by now, PRBS sequence becomes a built-in command in computer, so you don't need to write computer codes on your own. You can just make use of this library in system identification toolbox. Okay. Now, what we're gonna do next is we're gonna derive correlation function or covariance function. And we're gonna derive the spectrum. Okay, we're gonna end up at what we're trying to see is to see the pattern, okay, the shape of the spectrum of PRBS sequence. And in order to do that, we have to we will do some math here. Okay, now let's talk about the property. Whenever your PRBS sequence has a maximum length, and that length is given by 2 to the n minus 1. Okay. With all those possible sequence, if we look at the for example, suppose this is one possible state, we look at the number of ones. We look at the number of ones in the state. All right. Then we will see that in one period, in one maximum length, okay, because there's a number of possible states. If we include 0, right, the number of possible states is 2 to the n, okay. Of course, if we want to count how many of ones, it's going to be half of them. Right? It's going to be half of them. That's why in one period, your YT contains 2 to the n minus 1. And of course, if we look at the number of zeros, if we look at the number of 0, is going to be the same, right? Half of you know, possible entry. So it's 2 to the n minus 1. But because we exclude all the zero state, right? So we have to subtract 1 0. So we're going to use this fact in order to compute the mean, okay, and the covariance of Prbs. The second fact is that if you do the modulo sum between yt and some other term, some other, you know, yt minus k, but k ranges within one period, then the result is going to be just y at other times at t minus l, when l is the index between 1 and m minus 1. This is the second one. That's a proof, but I don't want to go to the detail. The book, the proof is in the book. Okay. And other thing, when you have the modular sum operation, okay, this identity holds. Okay, so x and y are both binary. This identity holds, and you can just verify it by just using the table. Okay. Just check, tabulate all the possible outcomes and see that both sides of the equations hold. Okay, now we're gonna use these 3 facts in order to compute the mean. Why do we need to compute the mean? Of course, the goal is to derive the covariance function. Okay, let me recall. If you review the video on the stochastic process, what are the covariance function? Can I have some definition? Can I get the definition? Totok?
Yes.
Yes. What is the definition of covariance function?
Expectation of, for example, x minus mean of x multiplied by x minus mean of x transpose in the field of yeah.
Can you be very specific, because this is covariance function at time gap tau. Is the expectation of x what x because x is a signal, x is a stochastic process.
Yes.
What I mean, is this what x at what time?
I'm sorry.
I mean, you cannot leave it like this, because you need to specify at which time this x is computed in order to compute the covariance at time lag tau.
Yes, yes.
Okay.
It's start using time index x.
Yeah.
xi
X what? X
t minus tau.
T minus tau?
Wait.
Ping. Can you answer that?
I'm not so sure, but maybe it's of tau.
Minus?
And then it's very moist. Also moist. And yeah.
What?
Also moiety plus tau. Yeah.
And then this okay, Muhammad, what is the second term?
or
Total, can you
Yeah.
answer?
cross xt minus xt also. Mu t.
Mu t, okay. With the transport thing is for vector process, all right? The most important one is of course, I want you to recognize that you take the expectation of two residuals, all right, two terms, but these two terms are shifted by time tau, and that gives you the the covariance function at time tau. Okay, next, what is the difference between covariance and correlation function? Kanatat?
This one I don't know.
You must review, okay?
Okay.
The reason why we want everyone to review because this is some background required by the course. Okay, can someone answer this?
Subtraction using mean. In
Yes.
we don't subtract with mean.
Yeah. Okay, very good. For correlation, we typically use the term R tau. Okay, we don't need to subtract. All right, the mean. Okay, this is the version for stochastic process. But then, as I suggest that you should read the book. Of course, if you have Thai book, read the Thai book. If you don't, international student, you can read it from the main textbook. Lung, okay, Lung also explained that. Okay, if you have a version that if you have a signal that actually is not stochastic. If it's not stochastic, of course, all the input signal we talk in the system identification process is not purely random, right? Just like the sinusoidal input we talked before, it is not purely random because you are the one who synthesized this, right? You determine the omega, you specify the magnitude, you decide the phase shift. Okay, so that's why the concept of autocorrelation, autocovariance will be done with the time average instead. Okay, everyone see the connection? The correlation here, this is for random process, right? We use expectation. But when the system is quasi-stationary, we use this term. You just check it out in the book, okay? That it means that the signal that has this limit, this limit is finite, okay? And then when we when we compute the actual autocorrelation, we just use the time average instead. So you see that when you multiply u at time t plus tau and ut, so this is like a time average version of this expectation. Okay, everyone is clear? Everyone's agree with this? So that's why we're gonna use that expression in order to compute the autocovariance function. Okay. Now, before we compute the covariance function, of course we know that the covariance and correlation are just differ by the means, like how you subtract the mean before computing the expectation. That's why, okay, let's compute the mean, okay, given by small m. The mean is, of course, for stochastic process, the mean, or we can use m, small m, is going to be expectation of xt. Okay, so when the signal is quasi-stationary, okay, we're gonna use the summation, sorry, the time average instead. So it's 1 over m summation of yt, okay, in one period. Then of course yt is your Prbs signal, right? Now, let me put a note here that now is a sequence of yt. What is yt? Yt is not the state of Prbs, but yt is the final output, which is given by the last state of Prbs sequence. All right. So yt is a scalar. Now come back here. So your yt is either 0 or 1, okay? And when you take the mean, if you sum of yt, of course yt is either 0 or 1, so the sum turns out to be, oh, just the sum of 1. Just the sum, the number of ones in yt, and then because of the results in the first property, that the number of ones in yt is actually 2 to the n minus 1, which can be expressed in terms of m. M is the maximum period of pseudo-random sequence, as you know, m plus 1/2. You put it back here, arrange a little bit, and then arrange it, and then the mean can be expressed as 1/2 plus 1/2 m. Does it make sense? Does it make sense? Yt is either 0 or 1. Okay. Ping, if you have a binary sequence like 0 and 1, like Bernoulli random variable, what would be the mean?
Then what can it should be 1?
No, what I'm asking is that, okay, this is the mean of Prbs output, okay, but I'm just gonna compare with binary random variable, okay. So the very first example we can think of is Bernoulli random variable, right? That has equal chance. The chance of occurring 0 is 1/2. The chance of 1 is also 1/2, right? Okay.
Yeah.
If you look at that random variable, what is the mean?
Oh, it should be half, I think.
Yes, the mean should be 1/2, right? But then, okay, now let's take a look at the mean of Prbs. Then you have 1/2 plus 1/2 m. All right. Then you have this extra term. So it means that, okay, when m is large, 1/2 m is going to be less and less, right? So your Prbs sequence, as you increase the number of states, the maximum period will increase. This term will goes down. So your mean, the mean of Prbs will close to 1/2. Just like a pure, you know, binary random, but pure binary random variable with equal chance. Okay, that's the first one. Now we're gonna look at the autocorrelation function C tau. All right, but of course let's look at the first leg. This is the 0 leg, which is represents the variance of the process. So we're gonna use the identity that for, of course, for a random process, right? The covariance at time tau at time 0 is going to be given by the second moment minus the what? The mean, right? The mean square. Okay, now that's why we for cosine stationary, we're gonna replace the expectation by the time average, and this is the mean square. Okay, and we do the same. The sum of y square, because y is binary. Again, the sum of y square and the sum of y would be the same, right? It would be the same. So this gives you the mean. That gives you the mean. And then because we already compute m from the first step, when you arrange it, everything, you have this final result. Okay, if I further arrange a little bit, I would get 1/4, right? Minus 1/4 m squared. Just like what I mentioned before. Again, if you have a binary sequence, 0 and 1, a binary random variable, each of them has a probability of 1/2. Napat, what is the variance of a random variable, of this Bernoulli random variable? Napat?
I don't remember, but it depends on time.
No, it's not about time. I'm asking about, a very simple binary random variable, right? That has equal chance, the probability is 1/2. Just 0 and 1, both of them has equal chance of occurrence. We Ping previously suggest that, the mean of y is 1/2, right? Now what I'm asking is, what about the variance?
Oh, okay. 1/4 ครับ
Yes, okay,
It will be
1/4.
then 1/4.
What's that?
It will be less than 1/4.
1/4. Right, 1/4, right. So in Bernoulli random variable, if it has a probability of success as p, the variance is p times 1 minus p. So when p equals 1/2, the variance is 1/4. Okay, what I would like to mention is somehow a relation to the Prbs that is not purely random. That's why we call it pseudo-random binary sequence. But turns out that the variance covariance at time tau gives you something slightly close to a pure random variable, because the covariance is just 1/4 subtract by other terms. That other term supposed to be close to 0 when m is large. Everyone agrees? Right? Like when m is big, this term decrease. So your covariance at lag 0 is close to 1/4. Just like the variance of Bernoulli random variable. We have about 10 minutes, okay? Now let's just finish the last one. When tau, what about tau at tau is 1, 2, 3, and 4? Okay, we just use the definition. We also use the relation that, okay, minus the mean, right? Okay, because for stationary process, the mean has to be constant. So the covariance and correlation just relate by this equation. So that's why the covariance at time tau. Okay, now this is for cosine stationary. You replace the expectation by the times average. So it's a correlation at time tau. You shift here tau. Okay, and then we use the third property. We use the second property. Okay, when you have I mean, you can express y at time t minus l as what? As the modulo 2 of yt at 2 different times. Okay, then okay, now let's see step by step. So this is what you have at the second step. And then, oh, I think you use the, sorry. I think we apply the third one first. Sorry. Okay. Apply the third one. You have the product of two binary sequence. You can express it into the right-hand side. All right. So now it's going to be the row of yt plus tau, all right, as x, and then yt as y here. Okay, so okay, use this identity, plug it back to the second step. Okay, but now let's take a look. If we look at the first term, what is the summation of this guy? City Park?
M plus 1 over 2.
M?
M.
What?
Big M plus 1 over 2.
Big M plus 1 over 2? I mean, what I mean is that, okay, this is nothing, but I mean, if you shift at time tau, these also represent the mean, right? Because you still make a sum over one period. It doesn't matter if you shift by time tau, right? No?
Yeah. So it's the mean M. Yes,
it's the mean. All right. So that's why you have two terms, and then it reduce to this term. Okay. And for the third term, the green one, we're gonna use the third property. Sorry, the second property, that the modulo 2 of yt at different times can be expressed by yt at y at other times. Okay, so that's why we can represent it like this. Okay, and then we just do the same. I mean, it's just yt plus other times index, right? But I mean, if you just look at this expression, it doesn't matter because you just shift by some index. So the result would still represented by the mean, right? So that's why this turns out to be m half subtracted from m. So you're gonna get m half minus m squared. Right? Everyone follow this? Like you have let me draw another example. You have something that has a periodic, right? Prbs sequence is periodic. So if you compute the mean within one period, would be the same as you find the mean of the shifted signal, right? As long as you compute the mean within one period. That's why the time shift here doesn't matter. As long as you compute the sum over one period, it will still give you the mean, which is m. And with the factor 2 here, you get m half. Okay, the result is this m half minus m squared. And you just plug it in the expression of m, small m, from this one, you get this result. All right. So let's sum it up. We take a look at the box in the red box, all right? The red box. Okay, so this is a Prbs sequence that now currently the output is either 0 or 1. But then you know that you can always shift or scale these numbers into 2 different values as you want. For example, if you want the two possible sequences to be -1 and 1, you just make a transformation -1 plus 2yt. Okay, so you just map 0 and 1 to -1 and 1 by using this transformation. Okay, now let me ask you, this is another review questions. If you make a transformation like this, which is called f-find, right? What would be the mean of y tilde? How is it related to the mean of y? Totok? Totok? Oh, Totok is gone.
I'm here, but I don't have answer yet.
You don't have the answer yet? Muhammad.
Sorry, ma'am.
The sequence yt and y tilde are related by the f-find transformation. Okay, there's some known results in random process in random variables that such f-find transformation will make a change in the mean and the covariance of y tilde. But what is that relation? So how the mean of y tilde change from y? Do you have the answer? Okay, how about Kanatat? Kanatat?
I also don't know this one.
City Park? City Park.
2 times to the mean of y.
Yes, okay. Please review. For those who don't, who haven't got the answer, please review. It's f-find transformation of a random variable. I mean, you just, we can show it real quick. You just compute the expectation of the whole thing, right? And that gives you, City Park, this is not correct, your answer. Expectation of -1 plus 2yt is of course -1 plus 2 eyt. Okay? The mean is actually given by the same f-find transformation taken on the mean of y. Okay? Okay, please also review that. What about the covariance of y tilde? My answer is, okay, the covariance of y tilde will be 2 square the covariance of yt. Just sketch how we derive this. This is not hard, okay. So it's gonna be a factor 2 here, square. Okay, by using this fact and property, okay, if you produce the PRBS output and you shift it into -1 and 1, the mean will be shifted to 1 over m. The covariance at time 0 will be shifted to this, and of course at other legs would be shifted to this. But then this is a very nice result, because you would see that all right, the mean of PRBS will be close to 0 if m is large, will be close to 1, again, when m is large, will be approximated as 1 over m. The covariance function of PRBS is similar to the property of white noise, because the white noise has autocorrelation as the delta function. This is covariance of white noise, which is exactly 0 when tau is different from 0. For PRBS, of course, you see some tail that is non-zero, but this number is very small when m is large. Okay, so I think that would be the very first characteristic that we derive in this video clip. That is the covariance function of PRBS. Okay.